Okay, fine. So we are looking at so basically in the last class we looked at sphere decoding, and today we are going to look at uh, array decoding. Okay, how an array can decode the code words. And first I will recall certain basic things. As you know, z2 raised to power n is a set of all x1, x2, xn such that xi belongs to z2. It's a binary vector space of dimension n, right? And a code is nothing but subset. C is simply a subset of z2 raised to power n, right? So we denote C by n, capital M and D. I think this notation is now you are familiar with. N is length, right? M is total number of code words, and D is minimum Hamming distance. Okay, so these are the three parameters. Now, in case of, so this is a known as binary. C is known as binary non-linear code. Non-linear code, right? Non-linearity means, if you take a vector x in C and y in C, and then x plus y, if you look at this belongs to C or not, we don't know. This may or may not belong. So this may not belong to C. Okay, so then it's a non-linear code, right? So there is no surety that the closure of two vectors is again in C. Then that code is known as non-linear code. Now a code is said to be linear. A code C is said to be linear if it is a subspace of Z2 raised to power n, right? It's a subspace. And so then in this case, C is called linear code. Linear code. And we denote C by a square bracket n k d. N is length as usual. K is known as dimension of C. Okay, because now it's a linear code, so it's a dimension, and D is the same thing as minimum Hamming distance. Okay, so that means C is nothing but a vector space. We know that is a k-dimensional vector space. So basically, C is nothing but a k-dimensional vector space of C of Z2 raised to power n, right? And it is known as binary linear code. Okay, binary linear code. Okay, now we know that I think in the earlier classes we have covered that any vector space has a basis. So the basis of C, suppose B is a basis of C. That means B will be a set of k vectors B1, B2, Bk, k vectors, such that so cardinality of B is k. Okay, and such that two conditions are satisfied. What are those two conditions? First, that span of B1, B2, Bk is C. Okay, and second, B1, B2, Bk are linearly independent. These vectors are linearly independent and they span the whole space, so it becomes a basis. Okay, now So there is a one also a convenient way of writing these basis vectors in what is known as generator matrix. So let me write it down it in the form of a generator matrix. So linear code can be described in the form of a generator matrix. Okay. So generator matrix of a linear code. Generator matrix of a linear code. Okay. How do we describe generator matrix of a linear code? So here we can write down all the basis vectors in the form of a matrix. B1 first vector, B2 second vector, and so on. So you can write it down like this. Bk. All vectors I can put it like this. So we know that there are k vectors. So k rows, k cross size of this matrix is k cross n. N is the length and k is the total number of rows. This is known as generator matrix. So what are the BIs? BIs are basis vectors. We put it them row wise, and this becomes a generator matrix. As an example, so I can look at the following code. G generated by 1011 and 0101. So this is 2 cross 4, k is 2, and you can see that because of the presence of the vector 1 0 and 0 1, these two vectors are linearly independent, right? So that means first condition I can check that lambda 1 times 1011 plus lambda 2 times 0101 is equal to 0 will give us lambda 1 is equal to 0 and lambda 2 is equal to 0. So these two vectors are linearly independent, right? They are the basis vectors. And if you look at the span of these vectors, this should give us C. So what is the span? So span of these two vectors, span of 1011 and 0101 will be, I can say that the span we can write it down like lambda 1 times 1011 plus lambda 2 times 0101, such that lambda 1 and lambda 2 are scalars in G2. So now there are two choices for lambda 1, two choices for lambda 2. There will be total 4 vectors, and I can write it down all those 4 vectors here. One vector will be 0 0 0 0 when both lambda 1 and lambda 2 are 0, 1 0 1 1, 0 1 0 1, and finally addition of both 1 1 0. There are only 4 vectors in the span. This is our C. So from the generator matrix, we can find out what is our C, right? Any question at this point? Any question? No question? That's fine. So now, so we know that from a given linear, and what are the parameters of this code? So we know that C is described by, it's a linear code, length is 4, dimension is 2 because k is equal to 2 here, right? And what about minimum distance? So I can look at the minimum weight vector here, which is 2 here. This is our n, this is our k, this is our. Okay. Now I am going to form an array using this. I'm going to form an array. Let us see some interesting thing I can do here. How do I form an array? I write down first all the code words 0 0 1 0 1 1 0 1 0 1 1 1 1 0, right? I write down all the vectors. Essentially I have added 0 vector to all the vectors. So this is, I can say that 0 plus C is this set which we are getting, 0 plus C. Okay. Now I take, so we know that the space, this is a subspace, C is a subspace of Z2 raised to power 4. There are 16 vectors. So I can take any vector of weight 1 in Z2 raised to power 4. So I take 1 0 0 0 plus C and see what happens. Okay. So 1 0 0, when I add it to C, what will be the first vector? 1 0 0 0, right? The second vector will be 1 plus 1 is 0 and 0 and 1 and 1. If I add 1 0 0 0 in 0 1 0 1, so I'll get 1 1 0 1, right? And if I add into the last one, I'm going to get 0, right? 1 plus 1 is 0, 1 1 0, right? That's our, this is a vector which is a part of Z2 raised to power 4. Okay. I have taken, which is not in C. This vector is not in C and I'm adding it to all the vectors in C. Similarly, I take another vector, say, of weight 1 0 1 0 0 plus C and see what happens. So this will, the first vector will be 0 1 0 0. Second vector will be 1 1 1 1. Third vector will be 0 0 0 1. Fourth vector will be 1 0 1 0. Okay. So that's good. Now look at another vector. So this is also a vector in Z2 raised to power 4. Take another vector as 0 0 1 0 plus C. And now you see what happens. First vector will be 0 0 1 0. Second vector will be 1 0 0 1. Third vector will be 0 1 1 1. Fourth vector will be 1 1 0 0. Okay. So here we get 16 vectors. Now it turns out that this process of forming an array decomposes the whole space, our whole space Z2 raised to power 4 into 4 different sets. These sets are known as cosets, or you can call it as coset. And this whole process is known as coset decomposition. Okay, coset decomposition. So by taking a vector of least weight and adding it to the C, we have decomposed the whole space into 16 space. These are all 16 vectors. You can see that these are all 16 vectors, which are actually, giving us, all the vectors of Z2 raised to power 4. Okay. So the first one is of course C. The first coset is nothing but C, because 0 plus C is C, right? So this is your C. First one is C, and rest is 1 plus C, 0 1 0 0 plus C, 0 0 1 0 plus C. So this is known as coset decomposition of the whole space. Now, before describing anything further and telling you how this array can be used for decoding, let me explain certain basic properties of this coset decomposition, so that we know actually what are the basic mathematics behind it before we describe to you how we can use them to make error correction. Okay. Okay. So I think whatever I have told you about the binary codes can be done for the query codes, means codes over finite field. So n k is our query code, means it's a subspace of f2 raised to power n, k dimensional subspace. Okay. C is a k dimensional subspace. So I can form what is known as, I can define coset of a code. Coset of a code. What is coset of a code? Now, A in FQN. Okay, and suppose A is not in C, because actually what happens if you take a vector in C, you will get because of the closure property, all the you will get the C itself. Okay, so that's why we are taking something outside C, then add it to C. We get A plus X such that X belongs to C. This is our Coset formation. This is the definition of Coset, and we have done the same thing, right? Initially, we took A is equal to 0, 0, 0. We got C itself. Then we took A is equal to 1, 0, 0, 0, and we got another set. Then we took 0, 1, 0, 0. We got another set. Then we took 0, 0, 1, 0, and we got another set, right? Using C. So this is known as Coset of a code. So the first property of this is every vector of FQN belongs to some coset. And this was clear because we have done the coset decomposition of the whole space, Z to the power 4. We saw that if you pick up any vector, it is in some of the coset, right? So what I'm saying that if you take any vector B, so I would say that, sorry, write it down in times this here. Yeah. What I want to say that every vector of FQN is contained in some coset of C. Okay, so let me prove here. If you take B to be a vector of FQN, then we know that B certainly belongs to B plus C. I can form a coset from B plus C. So B belongs to B plus C, right? So every vector, B is an arbitrary vector, it belongs to some coset. We are done. Okay, we are done with this proof. Second property, says that if B belongs to some coset, I am taking any vector in the coset. So I am taking coset A plus C, and suppose B belongs to A plus C. This implies that B plus C is same thing as A plus C. So if I take a vector B in the coset A plus C, so C is a code, A plus C is the coset of the code made by the vector A. Now if I take any vector inside the coset and add it to the C and form make a coset, it will coincide with the same coset. You will not get anything different. I mean, for example, in this picture here, if you take, here, look at this the second coset 1, 0, 0 plus C, and if I take say 0, 0, 1, 1 vector and add it to C, we will get the same coset, second coset. We will not get anything else. So this is the beautiful property of this coset. But we can here prove it. And how do we prove it? These are two sets actually, right? B plus C and A plus C. So I can prove it by the fact that I can show that B plus C is a subset of A plus C, and I can also show that A plus C is a subset of B plus C. If we are able to show that, then the two sets are same, right? Okay, so now we know that we can prove it. Since B belongs to A plus C, this implies that B can be written as A plus X. for some x in C, right? For some x in C by definition. Now let us take, now I am taking an arbitrary element of B plus C. So let us take B plus Y, or B plus C. So I want to prove this fact, this first fact, that B plus C is a subset of A plus C. In order to show that, I take an arbitrary element of B plus C, which is B plus Y. I'll show that it also belongs to A plus C, right? B plus Y belongs to this for some Y in C, right? Now, this implies that B plus Y, Y is another vector, will be, I can put the value of B, which is A plus X plus Y. Now this is same thing as A plus X plus Y. Now C is a linear code, X belongs to C, Y belongs to C, the whole thing belongs to C. That means you got B plus Y belongs to A plus C. We started with an arbitrary element B plus Y in B plus C, and we have shown that B plus Y also belongs to A plus C. So this implies that B plus C, this implies that B plus C is a subset of A plus C, right? The left hand side is a subset of right hand side. In a similar manner, I can show that A plus C is a subset of B plus C. I leave it as an exercise for you to show this. I will leave it as an exercise for you to show that other side is true. You just take an arbitrary element in A plus C. Okay, I think this is not properly written here. Okay, take arbitrary element in A plus C and show that it is in B plus C, right? So that way we get A plus C is same thing as B plus C. We are done. Okay, so it's very easy exercise to show that A plus C is same thing as B plus C. This is the second property. Okay, now we come to the third property. Third property says that cardinality of A plus C is the same thing as cardinality of cardinality of A plus C is same thing as cardinality of C is equal to 2 raised to power k. Okay, so you want to show this cardinality of A plus C is same thing as cardinality of C. So basically each coset has same size and is equal to the same size as the cardinality of C. In other words, so basically all cosets have same size. So what how do we prove this? If you take a map theta from C to A plus C as theta of x is equal to A plus x for every x in C, then this map theta is, one can show that it's 1 to 1 and on to, right? This implies that they will have the same cardinality. The cardinality of C is same thing as cardinality of A plus C. Okay, and since cardinality of C is q raised to power k, right? Why? Because C is k dimensional, right? And there are, I should write it down. C will be something like lambda times B1 plus lambda 2 times B2 dot 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 lambda k times Bk, where lambda i's belongs to Fq. Fq is a field with q number of elements. The total choices are q raised to power k. So cardinality of C is nothing but q raised to power k. Okay, that's this value. Basically, each coset has same size as q raised to power k. This is a very fundamental result. So last, in fact, fourth property now I can list. Fourth property. Fourth property says that two cosets are either disjoint or coincides. Either disjoints. So two cosets either disjoint or they coincide. There is no overlapping possible, right? That means if we take two cosets, either they are disjoint or they are same. So let us try to prove this simple fact. Suppose there are two cosets, A plus C and B plus C, and suppose they overlap. That means there is a vector common. So that means suppose there is some vector which is common to two cosets. Suppose Z is that vector which is common to A plus C intersection B plus C. Okay. This implies that Z is equal to A plus X is equal to B plus Y. Okay. For some X, Y in C. Right. And this means, B can be written as A plus X minus Y. So X belongs to C, Y belongs to C, so X minus Y belongs to C, so the whole thing belongs to A plus C. So that means B belongs to A plus C. If B belongs to A plus C, this implies that B plus C is same thing as a coset A plus C from our previous result. Okay, and hence cosets will coincide. If if we try to make something common, they will coincide. It is not possible to have overlap in the coset. So this is a nice property. Okay. Now we can define what is known as coset leader. Coset leader. So coset leader is a code word of minimum weight. Minimum weight in a coset is called a coset leader. Okay. So, for example, in our cosets here, these are coset leaders. Our let me see if I can make the color change. This is a Coset leader. Okay, this is another Coset leader. This is another Coset leader. Why? Because they are code words of least weight in each Coset. Okay, so these are nothing but Coset leaders for us. Okay. Now, finally, whatever we observed here in this example, that if C was a code and we form the cosets with respect to the coset leaders, we get the decomposition of the whole space. This thing we can write it down as a property. That's the last property. Last and final property says that our whole space FQN is nothing but 0 plus C. That's the first coset. Remember, union A1 plus C. That's the second coset. Union A2 plus C. That's the third coset. Okay. Union dot 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 union AT plus C. How many cosets are possible? I mean, how many T's will be there? So obviously, T will be Q raised to power n minus K minus 1. What is the reason for this? Because you see, again, we look at an example here. In this example, you can see that size of C is Q raised to power K in general, right? Size of C is Q raised to power K. And total number of vectors in the space are Q raised to power n. So, since it is a whole decomposition, how many such cosets will be there? Q raised to power, n minus K, right? Because they are equally decomposed. So in this case, so Q raised to power n divided by Q raised to power K, which is Q raised to power n minus K. Okay. For this reason, here T is Q raised to power n minus K minus 1. This minus 1 is there because 0 we have already counted here, right? So the counting starts from 0, 1, 2 up to 80. So this is a clear cut decomposition. So these are disjoint cosets, and this is a very, very important. And here AIs are normally coset leaders we take. Okay. So now we are actually ready to show you how this can be used to correct the errors actually. Now, before that, I think I have to cover a couple of more things like parity check matrix and so on. I already talked to you about generator matrix. Let me see if I can explain it to you. Yeah. In this picture here, if you look at it carefully, yeah. So suppose we send some vector here, how do we do the decoding here? Let me take some other color here. Suppose this vector is sent from here, 1 0 1 1 is sent. So your x is 1 0 1 1, and suppose last bit is corrected. Received vector y is 1 0 1 0. So how do we decode? We look at in this. It's really interesting actually, I should say. This example I have taken purposefully to show you, because the distance is 2. So how many errors we can correct? D minus 1 by 2. So 2 minus 1, 1 by 2. So we will not be able to correct any errors. So essentially, you know, if you want to correct the errors, sometime we will be able to correct, sometime we will not be able to correct. So I'll just explain to you that if x is sent as 1011 and y is 1010, so you see that 1010 is, this is our y, right? So normally what we say do, we subtract Coset leader from this and we will get this vector. So we will say that this vector was sent, but which is wrong. Okay, it depends which bit is corrupted. So suppose this was, suppose y is uh, y is first bit is corrupted 0011. Suppose y is 0011. So that means y is this. Okay, this is our x. Y is this. If y is this, then you can see that you know, it will be, so receipt vector y will be in some coset. I'll just check which coset it is. I found that it is in second coset, and I subtract the coset leader 100 from here, and we'll get the actual x vector. So this is how the decoding can be done. On the other hand, so essentially, because distance is 2, sometime we are able to correct the errors, sometime we are not able to correct the errors. If the first bit is corrupted, I am able to correct it, but if last bit is corrupted, I am not able to correct it. You know, we are getting a wrong result. Okay, so this is how we decode. In general, if distance is 3, we will be able to correct single error from this, you know. So how do we do that? X is sent from C. This is our C. X is sent, Y is received. So Y will be in one of the coset. Look at which coset it is, and then subtract the coset leader of that coset from Y, and you will get the X. This is how we decode all the time. Okay, and this principle works as long as the distance is, of course, you can correct the errors. Here, because distance is 2, so sometimes we will be able to correct, sometimes we will not be able to correct, right? I hope you got the idea about uh, Coset decoding. So basically, this is how we do the decoding. So that means if we have uh, if we have, if y is this, we are able to correct the error. If y is this, we are not able to correct the error, right? So sometime we are able to correct the error, sometime we are not able to correct the error, depending upon the code. This is happening because distance is 2. Okay, distance is 2 means we know that we will be able to correct d minus 1 by 2. T should be this much. Okay, so since d is 2 here, 2 minus 1 by 2 is 0, so t is 0, so we will not be able to correct error in general. Okay, but sometime we will be able to correct the errors even if, you know, the distance is 2. Okay, so this is the whole scenario of Coset decoding. Okay, so any question at this point about the Coset decoding? So we saw you know, what is sphere decoding. So I think now I should, you saw what is sphere decoding. Sphere decoding versus array decoding. Array decoding or Coset decoding. Okay, or Sripian decoding, it was given by Sripian, you know. So this is a very popular. So in sphere decoding, what used to happen? I can just do the analysis for you. So X was sent, Y is received. Then what we do? Y belongs to some sphere, and suppose T errors occurred. Okay, we know that if X is sent, Y is received, T or fewer errors occurred. So then Y cannot escape the sphere, it will fall into one of the sphere. So whichever sphere it is a part of, I will take the center of the sphere as the decoded code word. So I will say that, okay, this was the actual X which was sent. The center will be the actual X which was sent. In the case of array decoding, if X is sent, Y is received. In this case, Y belongs to some coset. So whichever coset it is, look at the coset leader and subtract coset leader. Okay, subtract coset leader to get the X. Get X. This is a basic difference between coset decoding and sphere decoding. Okay, so I think that's all for today. Actually, so I will not cover too many topics in the same day. So that's all for